Hello, everyone. My name is Austin Buchanan. Today, I'll be presenting work that's co-authored with my former PhD student, Hamid, who's now a postdoc at Rice. And he's on the job market if you're looking for someone to hire. Our talk is about political districting to minimize the number of cut edges. But first, what is political districting? Political districting is the task of splitting up, let's say, a state into districts for voting purposes. So for example, Oklahoma has 5 congressional districts, and each one of these districts had essentially the same population. I think they differed by 1 person. Another traditional redistricting principle is that districts should be contiguous on the map. They should also have somewhat compact shape. They shouldn't have a lot of tentacles going out to the sides. And also, ideally, we'd like to preserve political subdivisions. So counties, for example. So of Oklahoma's 77 counties, a majority of them are kept whole in this particular plan. There are a few exceptions around Oklahoma City and around Tulsa. Okay. So, but what is compact? How do you measure compactness? I think anyone looking at these 2 districts would agree that these are not compact districts. Here we have the broken wing pterodactyl in Maryland and goofy kicking Donald Duck in Pennsylvania. But if you try to quantify compactness, how would you do that? There's an idea going back to the 60s, a paper by Sid Hess and others, where they used the so-called moment of inertia to measure compactness. And if you use that as your objective, this is the plan you would get for Oklahoma, which mostly, I think, has compact districts. I think the one exception might be this yellow district that, despite not looking quite compact, according to moment of inertia, it fares quite well, in part because a lot of the population in this yellow district is around here, around the Oklahoma City metro area. Another measure of compactness, the number of cut edges that I'm talking about today, if you use that as your objective, you would get this map for Oklahoma. So I'll explain this a little more on the next page, but big picture here is to show that if this is your objective, you get pretty visually appealing districting plans. Now, whether this is a good map to enact in practice, that's a completely different question and not really the focus of this talk today. Okay, so what are cut edges? So first we have to talk about the graph. So we have this graph where each vertex, in our case, represents a county. And if 2 counties share a border, we connect them by an edge in the graph. If you've then partitioned the vertices into these 5 districts, like from the previous page, there will be some edges that cross from one district to the next. So those are the red edges here in the picture, and generally those are the edges that are cut. So here we have 40 cut edges, which is actually minimum possible if we require these other constraints, that we have 5 districts, each one is connected in the graph, and each district has a population between these lower and upper population bounds. Now, how do you come up with such a map? So here's the first MIP that I'll talk about, and it's maybe the one I think most people would write initially. So first we have these assignment variables that tell us yes or no is a vertex assigned to a district. And this is like a district number, 1, 2, 3, 4, all the way to K. We also have these cut edge variables that tell us yes or no is an edge cut. So again, we minimize the number of cut edges. Each vertex should be assigned to 1 district. District's population should be between those 2 bounds. And then we'll come back up here to these cut edge constraints. And they say, you pick an edge UV, and you pick a district number J. If U is assigned to district number J, but V is not, then the edge between them is cut. I haven't given any contiguity constraints here. We'll talk about those on some later slides. But if you solve this model as is, you'll get some computational results like this. These are all county level instances. So Oklahoma has 77 counties and 5 congressional districts. And you'll see here that the number of branch and bound nodes is sometimes quite large, which I think is partially a consequence of the really poor LP bounds. So you'll see here that the LP objective is always 0. There's a reason for that. We go back to our model and we set all of these x's to 1 over k. It will allow us to set y 0 here. In fact, that'll satisfy all of the other constraints. So the LP bound is really bad, which I think partially explains why the time is as large as it is in some cases. But there's also another concern, and that's the symmetry in this model. So if you assign these vertices to these different districts, the district number is kind of immaterial. It doesn't matter what number you give each district. So you can always permute the district numbers and come up with kind of a different representation of the same underlying districting plan. In fact, the number of ways that you can permute the labels is k factorial. So this symmetry is known to cause problems for branch and bound solvers, and it's something that we would like to deal with if we're trying to speed up our computation. And then last comment here is that even if you do solve this model and maybe it takes you an hour or more, it may return something that's not even contiguous. So point here is that it is important that you impose contiguity in your MIP. Another model that you might write is actually very similar to before with a slight tweak to the variable definition. So now we say that xij is 1 if this vertex I is assigned to the district rooted at vertex j. So not district number j, but the district rooted at j. This is a little convenient when writing some contiguity constraints, because if you know where the root of the district is, this can help you. And there's some small tweaks that you have to make to the constraints to make this variable definition work, but the ideas are pretty straightforward. And unfortunately, if you solve this model, you get even worse results. So the number of branch and bound nodes is somewhat large, except when it isn't. And when it isn't, it's because you didn't explore many nodes. You didn't, the computation did not proceed that far. It's still solving LPs. So you'll see even after a 1 hour time limit, you have a lower bound of 1. So 1 cut edge. We know this. So I think part of the reason for this poor performance is the really bad LP bound, but also the symmetry. In fact, the symmetry is worse in this model than it was in the labeling model. I'll let you think about that if you're curious. Okay, so if we want to solve larger instances, if we want to solve these instances more quickly, we've got to do something. So we have a whole bunch of tricks from the MIP arsenal that we propose to use. I'll talk about these latter 4 in a little bit of detail, but this first idea I think is very intuitive. If you have a solution that you know of, give it to the solver, inject that as a warm start. And so we actually use this Jerry chain software to do that for us, to find a heuristic solution. Okay, so the next thing we would want to deal with is the symmetry. And there's an idea from the graph coloring literature called the asymmetric representatives model. And it works like this. So we pick an ordering of the vertices. And we say that if you're constructing a district, we always want the root of that district to be whichever one of its vertices is earliest in this ordering. So one convenient way to impose this in the model is just to fix those variables to 0 whenever I comes before j. And we like to call this diagonal fixing because of this picture. So here we have the 33 counties of New Mexico on both axes. They're ordered in a particular way that we'll talk about how we got this ordering, but and then those entries that are above this main diagonal, we are able to fix to 0 with this idea. So we put a little d here in this table. And again, that fixes roughly half of these variables up front. The next idea is to exploit the population lower bound. So for example, after we've fixed our ordering and after we've done the diagonal fixing, if you look, let's say, at this last vertex in the ordering, that's Union County in New Mexico, population less than 5,000. That is actually the only vertex that can be assigned to the district rooted at Union County because of the diagonal fixing. But you can't build a congressional district with 5,000 people. So it can't be the center of a district. We can fix its associated center variable xjj to 0. And then likewise for this vertex 9, which is Roosevelt County, the same sort of thing happens. That you take the population of Roosevelt County and all counties that occur later in the ordering, you add up their populations, that's going to be less than L, so not enough. So you can't root a district there. But for vertex 8, the next one prior in the ordering, the situation is a little different. So here in blue, I've drawn all of the counties that occur later in the ordering than vertex 8. And if you add up their populations, you'll actually get something that's suitable. It's more than L. The problem is contiguity. There's no way to build a contiguous district made up of blue counties that reaches that population bound. The reason is the reachable vertices from 8s, they're only these 4 right here. There's a little one right there. So none of these could actually conceivably be assigned to the district rooted at 8. So after this, we get only these vertices, which I'm going to call S sub 8. That's the subset of these vertices that can be, I guess, occur after 8 in the ordering and also can be reached from 8. And now we look at these counties and we see, oh, it's actually less than the population lower bound L. So again, we can L fix this county. So that allows us to fix even more of these variables to 0. Okay. So this was all assuming that we had this ordering. That you'll see here, this ordering right where the L fixing starts. It's ordered 1, 2, 3, 4, 5, and so on. So how do we get this? And it's based on this lemma. If we have a subset of vertices B, we call it B because we put it at the back of the ordering. Suppose that B is such that every one of the components of its induced subgraph has small population. So in this picture of New Mexico, the B counties are the ones that are in white. So here we have 2 components, this big one and this small one. Both of those components have population less than L. So if we place those counties at the back of the ordering, then every one of them will be L fixed. It turns out that among all possible orderings, placing a maximum such B at the back maximizes the number of L fixings. So how do we get that large set B? Ideally a maximum size B. In our approach, we just solve this MIP. It's quite straightforward. I won't go through the details here. Other than to say we don't have to solve it to optimality necessarily, since we're only using this for pre-processing. And in fact, in our implementation, we just run it for a minute and just return the best solution that Groby has found up till then. I'll skip this for time. Okay, so these are the results that we have kind of for the pre-processing. So we talked a lot about this special subset of vertices B that we put at the back of the ordering, and you'll see that MIP that we solve to find it usually takes just 5, 10, 20 seconds. In some cases, it runs up into this 1 minute time limit. But even in those cases where it runs up to the time limit, the solution size B is actually quite close to the number of vertices, which is a natural upper bound. So they may not be optimal, but they're pretty close. So the size of B kind of directly factors into how many of these variables get L-fixed, which is a decent number, as is the number of variables that are fixed with diagonal fixing. And there are a few fixed with something called U-fixing that I skipped over, thus leading to the total percentage of X variables that are fixed, typically being 80%, 90%. And in fact, for these instances below this line, these are all tract level instances. I probably should have mentioned that. County level up here, tract level down here. For all of these tract level instances, the percentage of X variables that get fixed beforehand is 95% or more. Okay, our last trick is to write an extended formulation for the objective function. And it's essentially coming out of this paper from, it's a math programming paper from '96. And what it does is it takes those constraints that we had before, those cut edge constraints. Normally we would have a Y variable over here. What these constraints do is to rewrite this in a stronger way. So we have a new variable that tells us not just whether the edge is cut, but why is the edge cut. So this variable is 1 if the edge is cut because its incident vertex U is assigned to district number J or district rooted at J, whichever. But its other incident vertex is not assigned to that same district. So the edge can be cut in many ways depending on which district U is assigned to. Add that up over all the different ways, and that tells you whether or not the edge is cut in total. So if you use this model to kind of supplement it to the previous models, you'll get a much better LP bound. So, in some cases, let's say for Kansas, the original bound, LP bound was just, say, 5. But with this extended objective, you can bring that all the way up to 14, which is a huge improvement. Okay, so finally we have kind of the results for the whole shebang, all of the tricks combined. And so I separated into 2 parts. We've got the Hess-based model over here, the labeling model over here. And I should mention also all of the tricks that I explained for the Hess model can be extended to labeling with a little bit of effort. Okay, and then under each of these we have 3 different columns, and these are each for different contiguity models. We've got length bounded cut that we had proposed in a previous paper, single commodity flow, also proposed in the previous literature, and then these models of Shirabe from 15 years ago. And I think the big takeaway here is that they all perform about the same. There's not a huge difference between these different contiguity models. They all solve the same set of instances. They're never like an order of magnitude apart from each other. Not a huge difference. I think they're all reasonable choices. Another observation is that with the labeling model, we can solve slightly larger instances, just 1 or 2 more instances. So right around where we've got, let's say, 500 vertices is kind of the stopping point of what we're able to solve exactly. Okay. So in conclusion, I think cut edges, it's a nice way to measure compactness. It gives visually appealing districting plans. But if you use just MIPS out of the box, it's going to be slow. But with some tricks, you can solve instances up to, let's say, 500 nodes. You can easily extend what we've done here to measure the district perimeters, not just the number of edges that are cut. So the only change you would have to make there is to replace the objective coefficients. They're currently 1, just replace it by whatever the boundary is between 2 different geographic units. Of course, there's some coastline paradox issues you'll have to deal with, but it could be done if you had those numbers. And then once you know the perimeters, then maybe you could extend the approach to minimizing the Halsby-Popper score. And then as a last disclaimer, we're not saying that the maps that are coming out of our computational experiments are good or that they should be enacted. That's not the point that we're making in this paper. We're saying if this is your objective, if this is what you're trying to do, here's how you could do it. And maybe the maps that come out of it could be tweaked to where they would actually be good maps that you might want to enact in practice. So here's some links to our paper and the code. Here's a link to just a website on my page. That's just a collection of redistricting resources from the OR perspective. And then before I go, I should probably also thank Daryl DeFord, whose data we're using in this paper. So Daryl's one of the other presenters. So thank you, Daryl. And that concludes my talk.